Section 2.6, Polyatomic molecules. In this section, we'll use the valence bond theory to study the bonding of polyatomic molecules. Let's use water as an example. The oxygen atom has an electron configuration of 1s2, 2s2, and 2p4. In the 2p orbitals, one is doubly occupied. The other two p orbitals are singly occupied. So in valence bond theory, we say, well, these two singly occupied p orbitals can form bonds with other atoms. And this is the diagram. So you have, let's say this is 2px, let's say this is 2py. The 2px contains only one electron, so it overlaps with the 1s orbital of this hydrogen and form a bond. We have these two electrons being paired. And now this 2py again forms a sigma bond with this 1s orbital of the other hydrogen atom. Now we have two bonds. So it does explain that in water there are two OH bonds. However, based on this model, because 2px and 2py are perpendicular to each other, we predict a bond angle of 90 degrees based on the valence bond theory. Well, obviously it's wrong. Experimentally, the bond angle of HOH is roughly 105 degrees. So what's going on? The valence bond theory is further improved by introducing the concept of hybridization. For example, in methane, we hybridize the s orbital and the 3p orbitals, put them together, and then we form 4 sp3 orbitals. And each of the 4 sp3 hybrid orbitals interact with the 1s orbital of a hydrogen, and this is CH4, valence bond theory. And over here, this is just one sp3. Again, because in the p orbital, you have negative phases, you have positive phases. The positive phase is strengthened by the constructive interaction with the 2s orbital, and the negative phase is weakened over here. So again, this is just one of the 4 sp3 hybrid orbitals. There are 4 of them right here. And that explains in water, the bond angle is 105. Well, in water, you also have one s orbital and 3p orbitals. We again do hybridization. You get a 4 sp3 hybrid orbitals, and 2 of them form 2 chemical bonds with the 2 hydrogen atoms. The other 2, well, hold the lone pair electrons. And because lone pair electrons are more diffuse, and they push the 2 bonds a bit closer to each other. So supposedly in a perfect tetrahedral structure, the bond angle is 109.47. In water, it's 105 point something. Now let's look at some other hybridization schemes to form a linear structure. You can have SP hybridization, PD, or SD, and to have a angular arrangement, you can have SD hybridization. So in quantum mechanics, it's possible to write out a mathematical function for each of these 2 orbitals. And so-called hybridization is just to take the linear combination of the wave functions that represent the atomic orbitals. So now 3, coordination number 3. So we are familiar with sp2 hybridization. One example is ethane, CH2, each carbon has a sp2 hybridization. And then for coordination number, in methane, it's sp3, so that's common. sd3 is possible. And then coordination of 5, you can have sp3d, spd3. So basically you need to put 5 atomic orbitals together. And again, in quantum mechanics, it's possible to just take the linear combination of these 5 orbitals, and then we'll see they form, the right angles, the correct angles to form this trigonal bipyramidal structure. Octahedral, this is pretty simple. you just put one s orbital, 3 p orbital, and 2 d orbitals together. You form this octahedral hybridization. And I just want to let you know this S is spherical. This P3 is spherical because you're putting Px, Py, and Pz together in quantum mechanics. You'll learn that if you put them together, the shape is spherical. So this D2, you need to use 2 of the d orbitals. So if you pick 2 carefully, for example, you pick dz squared and dx squared minus y squared, and then you will see it has a octahedral shape. So of course you can put some other atomic orbitals together to form some other different shapes. For example, 3 p orbitals, 3 d orbitals. I believe this is just px, py, pz, and this one is dxy, dyz, and dzx. And you take the linear combination of the 6 wave functions, you can form trigonal antiprismatic shape.